So give a big applause to welcome Dave Elliot from Google on stage today.
Thank you. Thank you. And thank you for having me here. This is a fantastic turnout. I'm really impressed. And I'm also excited that following me, we've got Thomas, who used to be with Google Brain. So you're going to get a double dose of Google here today. Okay, so I'm Dave Elliot, and I've been with Google for about 4 years. And I'll say that I'm super excited about speaking with you all today. And what Michael said earlier is really true. I'm here for you. The reason that we're all here is because it's exciting to talk and really listen to the exciting, interesting ideas that you all have. So here's the quick agenda that I'm going to go through here today. I'm going to, because this is a keynote, Tom and Michael asked me to start with some really high-level concepts. The first opening question was how many people are familiar with, or how familiar are you with machine learning, with artificial intelligence? And some of you weren't. So I'm going to start with some very high concepts and move quickly through to what I was asked to speak about, which is specifically how does Google use machine learning to give some examples of products that we use and some of our customers that use our products to advance machine learning efforts. And then I'll finish with just a few comments on some of the challenges we're seeing and some of the opportunities we're seeing, perhaps for you to take advantage of, and some of the things that we're doing internally that you can take advantage of, things like Tensorflow. So with that, let's jump into it. So what is machine learning? Machine learning, you could say we're at the apex of inflated expectations, right? This is the new, right? This is the thing that fills a room like this with standing room only. And the challenge with that is, this is the chart from, I think, Forrester, showing that this is what most technologies go through. They go through this period of innovation, and then you get this peak of inflated expectations, and then it falls typically into this trough of disillusionment, this area where people think machine learning will do everything for them. And then the reality sets in that it's typically long, hard work. And this is how most new innovations go through. So machine learning, I believe we are at that peak of inflated expectations. But I also believe that there's some really good reasons for this. There's some reasons now that people are so excited about this. And I want to talk a little bit about those reasons. So let's start by taking a quick step back. And there's a 1,000 different ways to define machine learning, artificial intelligence, and deep learning, right? And those are really the interesting areas that, or maybe the directional path that we're talking about here. This is the AI summit, but artificial intelligence is just kind of a broad term. And within that, we've got machine learning, which is an area that I'm going to spend most of my time talking about. And even specifically more specific to that, you have deep learning. And deep learning is really where a lot of the excitement is. And I think we've got a couple of presentations here today, or at least one presentation on deep learning. So a simple definition, right? It's a way to solve problems without explicitly codifying, without writing code for the solution. And it's a way for systems to improve themselves. So, I'm a software guy. And when I was a kid, I wrote a sports program, a baseball program, and I developed all the different scenarios I thought were important. If a pitch is thrown this way and somebody swings that way, this is the result. And it was all math, statistics based, but it was coded. It's hard coded with a set of rules, right? And those rules were set. Well, as time went by, I realized I can make better rules. So if we were at a different elevation, maybe the ball would behave differently. So I had to go back and develop new rules. And as time went by, I realized more and more scenarios needed more and more rules. And that was terrible, right? Because I had to go back and keep developing those rules, right? Those heuristics were manually coded. And that is really how software has been developed for the last 20 or 30 years. And machine learning gives us an opportunity now to have an entirely new approach to how software is developed. So again, quick definitions. Machine learning is using many examples to answer questions. And I think this is really important as we think about machine learning and artificial intelligence. You need to have an idea of what you want to do. You need to have an idea of what questions you're trying to answer, what predictions you're trying to make. And then you need to have some examples. Another way of looking at it is data plus algorithms gives you those insights or those predictions, statistics plus programming. And really, again, going back to what I said a minute ago, it's because heuristics don't scale well. If you think about Google, right, we have 7 products that are used by over 1 billion people. And we have 1 billion hours a day of YouTube videos and billions and billions of daily searches. So creating these rules, these heuristics manually, can create millions and millions of lines of code that just simply doesn't scale well. So an example of this, is this a breakfast food or a pet? Now, to most people, this is tricky, and it's a little bit bright up here, but to humans, if you take a second, you can figure this out. So how would a machine learning model create a system to be able to make the determination on something like this? And I use that example because images, right, it's state-of-the-art, best practice. We're going to hear about language in a minute from Thomas. And these are areas that are, I won't say they're solved, but boy, we're getting close to being solved for image recognition, for computer vision. And deep learning, it's really model reincarnation. Deep learning has been around for I don't know, 20 or 30 plus years. But the modern reincarnation of it, or deep learning is a modern reincarnation of artificial neural networks. And what's new about it, more than anything else, is the ability to scale, right? The ability to use GPUs, the ability to use cloud infrastructure, to be able to do this at a scale that years ago were just simply impossible. And so some of the key benefits are that you can use raw, heterogeneous, you can use noisy data, and you can get those insights that in the past you weren't able to get. So an example of this is, again, looking at computer vision and an image, very simple. Is this a cat or a dog? So your input is pixels, and your output is a prediction, and you simply go through with this neural network, and you put weights associated with the images with the pixels that they're recognizing, and then you go through multiple examples and you change those weights. I mean, it's the most simplified version of it that I think I can share. So how's that applied in other things? So similar to identifying is that a breakfast food or a pet, or if it's a cat or a dog, we use this across now thousands of, well, not thousands, but probably 100 or hundreds even of products inside of Google, and we have thousands of models built over the last 3.5 or 4 years to do that. Why all the interest in this today? I think this was been spelled out in a lot of different presentations and a lot of different literature over time. Really, it's 3 things. The first is that what do you need to be successful? You need large data sets. And so today, we have more data than we've ever had before, and I think that's a trend that most people agree is going to continue. So you've got sensor data, you've got IoT data, you've got your phones. Everybody's got phones. We have more and more data today than we've ever had before. The second thing that makes machine learning more of a reality today is access to large-scale compute. So I mentioned this before. You can now jump on our cloud or Amazon's cloud or Microsoft's cloud and use thousands now, tens of thousands of compute instances simultaneously. And because machine learning is so computationally intensive, this opens up doors that just simply didn't exist a few years ago. And the third thing is you need what I'll just call smarts. You need powerful tools, and you need people. And I'll talk a little bit about that as a challenge going forward. So, but these 3 things, I think, we're seeing innovations across the board. You have access. You have really inexpensive GPUs. The cost of compute continues to be driven down. Both through innovations from NVIDIA, from the infrastructure microprocessors and also from the cloud players, NVIDIA. Power. So and you also see this with even things like storage, right? You store more and more data at a low cost. You're able to leverage tools now like Tensorflow, what I'll talk about as I'll talk about towards the end of my presentation. And then you have now again this access to this insane amount of data. So let's talk a little bit about Google and AI. So I'll spend maybe the next 10 or 15 minutes sharing some examples of how we use this internally. And let me start with a quote from our former CEO, chairman. Machine learning, this is the next transformation. The programming paradigm is changing. Instead of programming a computer, you teach a computer to learn something, and it does what you want. Right? This is the the vision, and this is why Google has invested so much in this as an area of focus. And furthermore, Google's current CEO has said, we're moving from a mobile, and he said this a few years ago now, from a mobile-first strategy, from a mobile-first transition to an AI-first world, right? That this is how we can dramatically improve how people live and work. And so this really is true. We think last time I looked, we had, 19 or 20,000 of our developers have gone through intensive ML training. It's a major area of focus, and we're applying this across, effectively all of our products. We think that this is so transformational that it's an area that we should continue to invest in. And so, if you look back just a few years ago, we were talking, you joined Google, and you said 2012, and so you look back in 2012, you may have been one of the only folks doing ML inside of Google, but then you look today, we have this is the number of models, something like 4,000 plus models inside of Google, and this just continues to be how we do business, how we develop software, for all the reasons I mentioned before. And you see the products that this is applied to. Just a few examples. Again, we've got 7 product lines that have over 1 billion regular users. Let me talk about a few of these. Search, right? Search is the most obvious thing. RankBrain is the number 3 signal for search rankings out of hundreds and hundreds of signals. And this is a fantastic use case where this is our core business. And even just small improvements can make a really big difference. And for us to be able to go and say, let me give an example. If somebody in San Francisco looks up the word giants, the result, based on rules, might be San Francisco Giants, the baseball team. But if somebody in New York City types in the word giants, the most relevant result for them might be the New York Giants football team. But if somebody in London types in giants, the most relevant result for them might be, big people, right? Really, really tall people. And it matters from where you come from. So you can create rules that say, if you're in San Francisco, show the baseball team. If you're in New York, show the football team. And then if you're in London or somewhere else, show big people. But that leads to the same baseball example I used before when I developed my own program. It's just more and more rules you have to write, where you end up with millions of lines of code. Alternatively, you could look at, because we have the data and because we have the compute, you can look at the historical data and create a system to learn that when people are in one place or another, and that's just one factor, right? Geography, they would get one result as a better result than others. So search has been a huge win for machine learning inside of Google. A second one, maybe not so obvious, we've applied machine learning to our own infrastructure. So we spent $27 billion in our infrastructure over the last 3 years. So it's a huge infrastructure investment. Huge, it's core to our business, how we deliver services to people. So we build data centers, we build networks, and we applied this to our data centers. We applied machine learning to our data centers, and the results were pretty dramatic. So this isn't just if you have 1 billion users and how to optimize their interactions, but we applied this to our own infrastructure, and we saved, basically, you can see here, this is when ML control was on, this was when ML control was off, and when you talk about cooling a data center, even small changes, again, when you've got so many large data centers of just tiny fractions of degrees as to when you cool things can make huge differences. And so this reduced our data center cooling energy by 40%. There's a white paper here you can go look at that explains how this was done. So we're applying this not just to our own products, but to our own infrastructure. Other examples, Google Translate. So this is a product that we've actually talked a lot publicly about the results of applying machine learning to Google Translate. And if you look at the phrase-based, which is how we used to do it, compared to neural, compared to human, you've seen some really dramatic gains, some really dramatic gains between by using human quality translation to compared to neural, compared to phrase-based. You've seen some really dramatic gains, and this is. I think the most interesting part about this is that it can be applied across languages, right? Once you develop a system that can learn the rules, for lack of a better term, of translation, then you can develop it across multiple languages. So here's just an example. And you can see this is a translation from Japanese to English from the snow of Kilimanjaro. And the things highlighted here are really the things that were pretty dramatically different. So this was the original Hemingway story phrase, and this was the old system, the phrase-based system. And so you can see close to the western summit, there's a dried and frozen carcass of a leopard, which it got cut off, explained what the leopard was seeking at that altitude. And the old phrase-based translation was, whether the leopard had what the demand at that altitude, there is that nobody explained, which just doesn't make sense. Now, it actually did a pretty good job for the rest of that translation, but that portion didn't make sense. And then with, predictably, with the new brain based translation, the last sentence is dramatically better. It's still not perfect. It left off an A, and it left off the, but the translation now actually makes sense. And I think you're probably going to talk a little bit more about this than I will, so I'll leave this to you. All right, so, and again, the last comment here is great because it can be applied across multiple languages, which again saves thousands of hours of development. Inbox, another product that has huge number of users. Inbox is something that we developed a smart reply option, which now 10% of mobile replies are from the smart reply. And basically, it's using the same machine learning mechanisms I discussed before. It learns from answers. It's a model that has been set up, and customers just absolutely love it. YouTube Watch Next. So again, I mentioned there's 1 billion hours a day of YouTube videos watched, which is astounding. And so the recommendation of what you watch next is really important. And in the past, there would be rules that were set that said, hey, this person saw this video, and the videos that are like this are this. Instead, we now have a system that generally looks at, again, what other people with similar profiles have looked like in the past, and it learns and continues to optimize the rules. And just a small change. I think we increased the daily viewership by 250,000 hours, which sounds like tons of hours to me, but I guess as a percentage of 1 billion hours, it's not that big. Google Photos. Who here uses Google Photos? Anybody? About half the room, maybe. Google Photos is amazing. It's amazing because you can throw your stuff in there and you can find what you want. And I got 30,000 images over the last 15 years or so, digital images, since the invention of digital cameras. I've just thrown it all into Google Photos. And now when I want to go back and find pictures of my daughter when she was 3 years old, and she's now 15, it knows what she looks like across those years. Again, these are all manifestations of machine learning that we've used internally. AlphaGo. Anybody who follows machine learning or artificial intelligence probably has heard this example. Who here has heard this example? Everybody. All right. Moving on. So, Pedestrian. Pedestrian detection. Actually, you know, the AlphaGo example is a really good one because it's so simple. Everybody knows it, right? It's so simple. We had the machine learn from a data set of 30,000 online games, and then it went and played its, 100,000 online games, and then it went and played itself 30 million times, and that was a first model. And then it just improved from there. And you know, playing itself 30 million times, again, going back to the massive amounts of compute that, that maybe you needed in the past, is something that is relatively trivial by today's standards. Going back to computer vision, pedestrian detection. I like this because this is the Google, the Waymo self-driving car, and it needs to be able to identify people, right? A self-driving car driving down a freeway by itself, or maybe with other cars, is really quite simple compared to being able to identify that, you know, it's Halloween and there's a kid dressed as an orange, and that's a person, and that they need to behave. It needs to behave as if that's a person. And this is, you know, these are much harder problems that make things like self-driving cars much more reliable. And you know, Waymo now has, I think, 3 million miles driven, and it's I think most people agree it's a pretty safe alternative, and it's only going to get better. So another example, and this is something that there's lots of examples like this. I like this one. It's ours, and it just shows the, you know, the fantastic potential. Diabetic retinopathy is the most common form of preventable blindness in the world, and this is for people who have diabetes, and if they don't get it diagnosed and treated, then they can go blind. Well, the problem is in many developing worlds there aren't enough ophthalmologists to do the examinations, to look at the slides, to be able to make the diagnosis. And so what the Google Brain team did was went back and they took thousands of images, and they hired a bunch of ophthalmologists to go through and to create the data set, right, to be able to identify on a scale of 1 to 10 how likely it was that, or how severe this disease was, and then they trained the data set, and ultimately they improved and improved and improved the model to where it is, you know, as good as or even better than the average ophthalmologist in identifying this. And this makes, you know, creates an opportunity now with millions of people who could go blind to create a you know, scalable system. And there's lots of examples like this. Can you find the cancer in this slide? You know, this is what pathologists do all day long, right? They sit and they look at these slides, and they make their best prediction as to whether or not this is a cancerous cell. And the Google Brain team's now working with a whole host of folks, and there's lots of folks actually who are doing these types of things. But it's really exciting, right? It really creates an opportunity to improve people's lives. And then finally, this is a commercial example. And this is a company that uses our infrastructure, which I haven't talked about, but Airbus has a satellite imaging business. And if you look at the images, and you can't really see it here, you know, this is, you know, a question is this snow or is it clouds, right? What's the white? And it's important to be able to know the difference, because things like forecasting crop yields, you know, depend on weather. So, you know, going back and being able to create a system to be able to help identify this visually, again, using computer vision, something that Airbus has been fantastically successful in. All right, so moving forward, there's lots of use cases, and I think we'll make this presentation available to everybody so you don't have to read all of these, but there's lots and lots of use cases. In fact, you'd be hard-pressed, and I don't want to sound like I'm super hyping it here, but you'd be hard-pressed to find many decisions that, many workflows that couldn't in some way improve by leveraging different uses of machine learning. From manufacturing, through retail, financial services, energy. I talked a little bit about how we use it ourselves to improve our energy yield. So lots and lots of use cases. So now let's talk a little bit about the challenges, though. So and how Google is, what types of things Google is doing to address those challenges. So going back to what I said before, there's 3 things you really need to be successful, right? You need lots and lots of data, you need the ability to have lots and lots of compute, and then you need smarter models, right? Powerful tools and frameworks is what we call it here. And that third one also is more than just powerful tools. It's also, you need the people to be able to leverage those tools. And I think we were talking about this last night, and we said, you know, there are thousands of companies doing this now, and it's really exciting. But there's probably tens of millions of companies that could benefit from doing it. And so it's that transition from where we are to that mainstream realization is what we want to be able to see. So a few ways that Google's helping with this. The first is Tensorflow. So Tensorflow, it's an open source project, and it's great for designed for deep learning. The difference between, or what I think differentiates, in my opinion, Tensorflow more than anything else from other open source options is that it was really designed for software developers, right? It was designed because it was, at Google, we're a bunch of software developers. We not so much experts in machine learning until, you know, we hired guys like Thomas 5 years ago, but we're really good at building software. And so that TensorFlow is designed for software developers. So that makes it more easily integrated in with solutions. So it was released November 2015. This is built and managed by the Google Brain team. The goals. First, establish a common platform. Second, become a platform that everybody can use. And third is make it the best possible options. And there is a significant investment. I think you were talking earlier about how Google tends to put many things into the open source community, and this is a huge investment by the company. There's lots of people whose only job it is to build and support this infrastructure. You know, I think you've seen the rapid development since November of 2015. This is just, you know, one of many tools or examples of how popular it is. Really hard to see, but this is GitHub stars, and it's actually now, this goes to March of 2017. It's now, I think, 67,000 stars, and you know, compared to Linux, Linux has 45,000 stars. So TensorFlow has really been greatly adopted, I think, since November of 2015. Oh, my favorite example of this, and I don't have a ton of time, but a Japanese farmer, small Japanese farm, you could see the mother and father here, manually, they were growing cucumbers. You can see this is their farm, and they needed to manually sort the cucumbers. And they needed to identify, this is ready for market, this one's bruised, this one needs more ripening, this one may have an infestation, needs to be thrown away. So I think they had 8 different categories that they needed to pick the cucumbers and move them into. And it was a small farm, so they were manually doing this, and it took them a ton of time. So what the son, the bright son back here did, was he knew a little bit of Python. He wasn't a machine learning expert, but he knew a little bit of Python. He went and he took TensorFlow and he applied it to this problem. And again, computer vision is something that is really, I won't say solved, but it's very close. He took images of lots and lots of cucumbers, took photographs, and then he fed that into the model, and he used transfer learning and was able to build a system that could identify which ones needed to go where, and then he just built a super simple conveyor belt with a camera on it. He used like a Raspberry Pi, an Arduino processor, and he created a way that these cucumbers would go out, the camera would look at it, make a determination, and then it would send it one way, another way, or another way into 8 different categories. You know, cost him, a few $1,000s, perhaps, to build this thing. And again, he knew a little bit of Python, he was a software guy, but not a machine learning expert. So we talk internally, and a lot of companies now, Microsoft, IBM, talk about the democratization of machine learning, and I think this is an example of it. Right? You don't need to have a PhD. It's great if you do, but if you think of the challenges, those powerful tools and those knowledgeable people, things like TensorFlow make it more realistic that you can do things like this. Also, let's talk about the future. You don't have these tens of thousands of PhDs like that you might need to be able to do this. We have something, we're working on things internally where we use, I guess we're learning to learn, right? The machine is what we're calling automated, or what folks are calling automated machine learning. So in the past, you've got, the solution requires machine learning expertise, again, which is at a huge premium. We don't have that much expertise, not what we need compared to the opportunity. You need data and you need computation. So what we're thinking instead of what we're trying to do instead is have the solution be data plus huge amounts of compute. And so what that might look like is basically you might have a controller here that this is just a super simple architecture. You generate tens of models, you train them for a few hours, you use a loss of the generated models as reinforcement learning signal. And it requires, I guess because it's a little bit sloppy and inaccurate, but it requires lots more compute. But the net result is that you don't need as many of those experts as you would in the past. So learn to learn, auto ML, is something that I think you're going to see more and more of. And early signs are super encouraging. And now, because you're able to do that, you do need that 100x compute. So other things we're working on here are custom-built ASICs, what we call Tensorflow processing units. Again, we're not the only ones working on this, but I do think this is a really exciting area, solving some of these problems around needing massive amounts of compute. And it really comes down to the cost of compute, right? And so we're working on TensorFlow processing units. It turns out, without spending too much time on this, CPUs are really well designed for precision. And as you think about doing computation for machine learning, it doesn't need to be quite as precise. But really needs to be cheap and fast. Second problem, or second issue with general CPUs or even GPUs are that it turns out that for machine learning, deep learning algorithms require matrix and vectrix operations. And so we're building these TensorFlow processing units to be really, really good at that. So we announced these last year, and you can see they're really, really big, 180 teraflops of computation, 64 gigs of memory, and they're designed to be connected together, running on our super fast Jupyter network platform. And they're really, really big and really, really fast. And again, they're designed to be networked using native ultra high-speed interconnects with tons and tons of compute and memory. TensorFlow processing units. You can use them via Google Cloud, the team I work for. I will finish, I think I have about 2 minutes left, by saying that we have a program we announced, I think, just a few months ago for academia, where you can go and use these for free. So talk to me afterwards if this is something that you're interested in. I'll leave that up there for a second for those taking pictures. Okay, and then the final piece here is, how do you work with Google with machine learning? And this is probably the closest thing you'll get to a pitch. There's 3 different ways generally that companies work with us, that people work with us, that individuals work with us. On the far left is TensorFlow, and this is designed for people who really are willing and interested in getting their hands, probably most of the folks in this room, getting their hands dirty in working with developing models and optimizing those models. In the middle is a cloud machine learning engine. So this is infrastructure outsourced as a service, where you don't need to necessarily build and manage your own clusters, for instance. You can still, if you want, develop your models on your Jupyter laptop at home and then go run it at scale on our own infrastructure for both for training the model and for predictions. And then finally, on the far right is machine learning APIs. And this is an area that what we've done basically is taken our models, but also the data, and made them available via APIs, things like computer vision and translation and speech-to-text And these are things, and most recently video, which is super exciting, super hard problem to solve. But so you can leverage our APIs and be able to identify and translate those types of things. So those are 3 ways that generally people work with us. And there's some examples of each with TensorFlow, Cloud ML, Cloud Machine Learning, what we call it, and then finally the ML APIs with things like computer vision and translation, speech and language. And so on the horizon, some of the areas that I think you'll hear more about from us in the next period of time. Kaggle. How many people here are Kaggle users? Okay, good. So now I want to go back and do my presentation over again, realizing that you're so sophisticated. Kaggle's a huge area of investment for us. I think that you'll see not just community built, but ultimately, maybe things like marketplaces develop that you can take advantage of. TensorFlow will continue to be an area of focus. Cloud and cloud machine learning. TensorFlow processing unit, TPUs. Things like AutoML, I mentioned before, really exciting area right now. And so these let me finish with some resources. You can go, most of the examples I gave have been written either as white papers or at least technical blogs. So you can go and see how we did things. And it's an opportunity for you to learn from us, and we love the opportunity to learn from you. So with that, I think I am out of time.
Thank you very much, Dave. We're going to have a few minutes for questions and answers. We're going to do a few questions from the audience and some of the Slido questions. I see there were a lot posted there already. One question was whether we're going to provide the slides. Yes, we do, right? Okay, and then
I love those questions. Those are so easy. Yes.
Okay, wait, let me switch here to the screen. Yeah, okay, this one we got. So another popular question was, cat recognition is great, but what about the other time series predictions? Wait, where was it? Let's fix it. The top question now. Yeah, maybe machine learning algorithms are better in categorization. Do you have a take on that?
Yes. What I was trying to share, I think, was examples of how we used it internally. That's all.
Okay. Yeah. Then we have this question here. What's the outlook for on-device inference at Google? Utilizing the device's compute power seems to be a big opportunity to improve users' privacy.
So it's a really interesting topic because the training and even to a large extent the predictions are so computationally intense. Doing that on a on-device, mobile device has a set of challenges. That said, we have taken TensorFlow models and put them out on Android and have had some success there. I think that it's as we continue to walk down the path, there'll be more and more things like this. I didn't think of it from a privacy perspective as much as a performance perspective, but I can see it from both angles.
Okay. Maybe one more from here, and then we look into the audience whether someone has a question. What metrics do you optimize when you try to optimize search with machine learning?
That's a very specific question. Yeah, I'm not sure I can answer that. It's a complicated question.
Any metric that comes to mind?
Well, I mean, I think at the end of the day, relevancy for the user, and there's, I think, some pretty well-established results of that. or studies of that as to different search metrics. And the other thing is always performance, right? And that's a little bit different, but usually it's relevancy, meaning click-throughs and things like that.
Do we have questions from the audience that didn't were your?
You ignored my question. That's the second one.
You're anonymous. Okay, let's do this one. How do you train your computer scientists in machine learning at Google?
Okay, so that's actually really good. So we taking from the premise that most of our developers are software developers, we've developed a whole host of internal training. But generally speaking, we've got a jumpstart course, which lasts 6 weeks long, that developers go through. We've got a short version, a 2-day version. We've got a 2-week version, and then a 6-week version that developers can go through, and it's everything you would expect a developer that would need to know in order to be able to apply machine learning internally. So it's not just generic machine learning, but also machine learning tools and resources that are available to them as a developer inside of Google.
Maybe an add-on question to that: are you hiring?
We're always hiring.
You're always hiring.
We are always. And in all seriousness, we are we.
Are you firing?
Based on recent developments, I probably shouldn't talk about that.
Do we have another question from the audience? There's Alex just behind you. There's a person.
About the
Microphone.
About the AutoML program you had running internally, what are your goals with it in terms of the scope of its capabilities, and do you think it's going to be a danger to the job security of machine learning researchers?
Yeah, so the question for those who didn't hear it was, what's the objectives of it? And then, will it be a danger to people developing ML models themselves? So the objectives are to try to be able to be more optimized in developing models. Again, we think that there are thousands and thousands of opportunities, and we need to be more efficient in developing those models. And there's a chronic shortage of really high-skilled resources to be able to do that. Do I think that will impact the career or the industry? Not really, because again, there's such a shortage of people who know how to do this. I think that like anything, automation will come, but there's just such a shortage and so many opportunities. We were talking about this last night at dinner. It's hard to stay focused on one thing because there's so many opportunities that exist for people who really know what they're doing.
Thank you very much, Dave. Big applause again for our first speaker. And I hand over to